Yes, sir. Good morning, sir.
Okay, good morning.
Yes, sir.
Okay, so I think we have enough participants, so let us start. Let me recapitulate what we had started discussion on in the last class. We were discussing the response of a single degree of freedom system. And for a single degree of freedom system, the response is being calculated with the help of the techniques of transform calculus. That is, we first transform the variable to by Laplace transform, that means to a complex domain, and then get the solve it and then transfer it back to the real domain. So that is the way we are doing it. Of course, um, there are of course other ways to solve the same problem by just using the theory of ordinary differential equation, which you know already. But say I am using this technique because it is a more general technique, more generally applicable a systems, different physical systems in general. So let us proceed with our earlier discussion. Okay, so our task was to calculate, find out the response of this equation with the initial condition x at t equal to 0, x0, and x dot at t equal to 0, as let us say v0 or initial velocity. So this is the initial velocity and initial displacements. So we found out that xs, so xt will be inverse Laplace transform of, this is what we have shown, that is s x naught plus v naught divided by s square plus omega n square.
Sir, equation is not visible.
Yes, equation is not visible. Maybe then, oh, I get it. See, so we said that um, so here if I take the Laplace transform, this will be m is then x0 uh, xs square minus sx0 minus b0, where the initial conditions are x t equal to 0, this is x0, and x dot t equal to 0, I name this as v0, that is the initial velocity. So this is what we have, and this plus k xs, this equal to fs, taking the Laplace transform, and we get that xs will be equal to, so xs will be equal to then s x naught plus v naught divided by s square plus omega n square plus fs divided by m times 1 by s square plus omega n square. So this is the Laplace transform of the response xs. And we have shown that the first part, so if you take the Laplace, so the inverse Laplace transform of this part, this will be equal to a cosine omega n t minus phi plus the inverse Laplace transform of this quantity, that is 1 by m fs divided by s square plus omega n square, where a is the amplitude, that means this will be x naught square plus v naught by omega n square, and tan phi will be equal to V naught by omega n x naught. So this part we have found out. Now you see one thing here. The response, this is actually separated into two parts. What is that? If we have, suppose if we do not have ft, so if I take temporarily ft equal to 0 and only the initial conditions, then this will be the response. This part will be the Laplace transform of the response, only this part. And if we take only, so this part actually represents the response due to the initial conditions. Okay, so maybe the response which we give for unforced situation if we give only the initial conditions. So this is response generated by the initial conditions. And this part, what is this part? This part is the response due to force alone with zero initial condition. So if I take initial conditions x0 equal to 0 and v0 equal to 0, so this will be the Laplace transform of the response only. So this part denotes the response of the due to force with zero initial condition, and this is the response due to the initial conditions without any force. So this is zero force response, and then another is the zero initial condition response. Now this is true for any linear system. In a linear system, the response can be broken down into two parts. One is that due to the initial condition without any force, and another is the due to the force with zero initial condition. So this clear separation is possible only for the linear system. Now I have drawn the this response can be drawn easily. So this part of this response, a cosine omega t, this is something like this, where t and this will be 2 pi by omega n, 2 pi by omega n, and this part we can say that this will be equal to phi divided by omega n, phi divided by omega n, where the amplitude becomes actually maximum. So this is a cosine phi, where x equal so a cosine phi, and this is equal to x0. So this is the response only for the free vibration. Free vibration means that there is no force present, only the vibration is generated because of non-zero initial conditions. Okay. So that is what we have. Now we are interested in finding out what is the response due to this part. Okay. Is this clear to you? There is nothing new. I taught it in the last class, so therefore I can proceed. So what I am now considering is so one part, you see that this xt has one part, let us say I call this f free t, which I have already shown, and the other part is the Laplace inverse of 1 by m fs times s square plus omega n square. Okay. All right. Now let me consider this term. Okay. 1 by m. So 1 by m is square plus omega n square into fs. So this is the term we have. Now you see, this term is actually only the force. And what is this term? This particular factor is only the contribution of the system. Okay. This comes from the force, external force, and this is the contribution for the system. Now it is sometimes useful in many situations. We may write down this. So this is the response, what I am saying, this is the response, and which is due to the force. The input is given as a force, and this part becomes the response, and this term which is inside the box, this denotes the contribution of the system, how the system is behaving. Okay? So this depends upon the system, the input depends upon the external force, and the output is the result. So this, what is there inside the block. Do you know the name of this particular factor? Particular term?
Transfer function. Transfer.
This is called transfer function. Who said this? Your MTech or dual degree?
Dual degree, sir.
Dual degree, yes, because you have learned it. Now, for the MTech students, you will slowly learn in your automatic control class. You are having automatic control this semester, isn't it? MTechs?
Yes, sir.
Yes, sir. Yes.
So, you will learn what is this called? This is called the transfer function. Transfer function of the system. So, what is the definition of the transfer function? Who said earlier? Can you now?
Yes, sir.
Tell the
So
class
like
what
when
is
we
it?
have
Yeah.
when we have zero initial conditions,
Zero
then
initial condition.
then like the input gets multiplied with the transfer function to give us the output.
So what is transfer function? You say this you will learn the text. What is transfer function? Transfer function is the Laplace transform of the output divided by the Laplace transform of the input with zero initial condition. Okay. So it is, so many students say it is the output by input or output function divided by input function. It is not. It is the Laplace transform of the output function divided by the Laplace transform of the input function with zero initial condition. That means x0 equal to 0 and x dot 0 equal to 0. So all the zero initial conditions are needed. So the Laplace transform of the output divided by the Laplace transform of the input, this we call the transfer function. Anyway, this we will learn later on. There is no need of special discussion on this transfer function. But what we have now, this part, so we have Fs and what we have 1 by m square plus omega n square. Okay, this one is the Xs. Okay, now what will be the xt for that? What will be xt? If I denote this by let us say s, maybe the name why I am writing s, it will be clear, but let me name this as xs. So the contribution, because of this part, I name as xs. Okay, so xs, what will be xst? xs is this is equal to f times 1 by m square plus omega n square. So what will be xs? xst.
Inverse Laplace transform of the
Inverse Laplace. What is this inverse Laplace transform?
Tan omega t.
What is the inverse Laplace transform of this function?
1 by sin omega.
1 by omega n square sin omega t. Omega n t.
1 by omega n square sin omega t. And what is the contribution
No,
of
no, sir.
this?
Like
Convolution,
always
sir.
comes into picture.
Okay, so there is convolution integral. So what we'll have to do, we'll have to find out the inverse Laplace of fs, which is of course ft, because fs was the transfer function, Laplace transform of ft. So I need to take ft. So what it does is that I need to consider ft and this operator, what I am writing, star denotes the convolution. I'll just, you know already, but let me also write it. So ft star, and what is the inverse transform of this part? What is inverse transform of this? The second part.
1 by m omega sin omega t.
1 by n omega n sin omega n t. Okay, n you should not forget, because n is the natural, omega n denotes the natural frequency. So this is the convolution of these two functions. So how do we write down the convolution?
Sir,
Now,
1 by m omega n square.
omega n square.
Sir, the answer ft into 1 by m omega n square sin omega n t.
Why omega n square?
Sir, because omega n square will come in the top and on the
No.
bottom.
Sin omega t, Laplace transform of omega sin omega t is omega n by s square plus omega n square. Laplace transform of cosine omega t is s by s square plus omega n square. Laplace transform of sine is sine. So this I should write down this Laplace transform of sine omega t. This is equal to omega divided by s square plus omega square. This result must be known to you. It is not omega square, not that. It is omega only. Okay.
Okay, sir.
Getting it. So please check it. I mean, you definitely have learned, but just recheck this. You correct yourself. It is not omega square. This is omega only. So therefore, m omega n and sine omega nt. And how do you write down the convolution integral? How do you write down this convolution integral here? Convolution integral of two functions. This will be 0 to t either f tau sine omega n t minus tau d tau divided by n omega n or 0 to t f t minus tau and sine omega n tau by n omega n tau. Either t minus tau appears in this function or t minus tau appears in the other function. Okay, so this is the definition of the convolution integral. So now we can write down. I assume that this part is known to you. You know how to write down the convolution integral. Okay, convolution of two functions. How do you write down in this integral form? This is the symbol of convolution. But when you write down the functions, then this becomes the function itself. So f tau sine omega n t minus tau, of course omega by m omega n is appearing, and integral over d tau, and sine f minus tau sine omega n tau divided by m omega n tau. So tau is appearing here, so d tau. So here, if you write down, let me see what is the implication of this part. So I have the force function is 0 to t 1 by m omega n sine omega n t minus tau into f tau d tau. So this is the response only due to the force with zero initial condition. Now let us see whether we can have a simple interpretation of this function. Okay. Now you will see that this function, this part which I have underlined, this particular part, so 1 by m omega n sine omega n t. What is the name of this function? 1 by m sine omega n t. What is the name of this function? Those who have definitely have already had certain exposure to vibration. So can you recall sine omega n t by omega n?
Is it impulse response?
Unit impulse response. It's not impulse response, unit impulse response. Unit impulse response. Now, unit impulse. So what it says that suppose I have what is impulse? Impulse is actually definition of impulse is actually ft dt over 0 to t. Let us say this is defined as the impulse. Okay. So what it says that this response is due to a force which is of this magnitude, which is this impulse. So and that impulse is unity. So unit impulse means that this is the impulse and that must be unity. Now this impulse is actually given over so small time. So let us say we have this impulse over delta t, time maybe let us say delta, and I give an impulse over this time delta. The impulse is 1 by delta. So the magnitude of this impulse, so therefore ft I am drawing. So this is over a time interval delta, and its magnitude is 1 upon delta. So the area under this curve, which is nothing but the impulse due to this force, this is nothing but unity. So area is unity. So this force is actually an impulse, unit impulse. So the impulse is actually having unit value. So impulse is unit value. Now here what we are actually saying is that this impulse, so therefore delta, if I now consider limiting to 0, so if I consider limit delta tends to 0, delta tends to 0, so therefore what will happen? This part actually, the magnitude will go on to infinity. But what is the uniqueness of this? That the whatever be the value of delta and the height of that one, the impulse of the force is exactly equal to 1, because this is delta and this is 1 by delta. So it is going to 0 and it is going to infinity. So therefore the product is becoming the finite value equal to 1. Now this particular function, where it is defined over a very small time delta, and it has a very large magnitude, satisfying the condition that area under this curve is 1, this is mathematically denoted as the Dirac delta function. Okay, Dirac delta function. This is this is the Dirac delta function. That means that over a time interval, delta, I am applying a very large force. So it is like in the physically, it can be done by just hammering the system. Just you take the hammer, give a hard blow to the mass, then we can approximately say that we are giving an impulse, because the hammer is actually in contact with the mass for a small time, but still we see the appreciable motion. So therefore some amount of momentum transformation is taking place in the system. Okay, although the time during which the impulse was given is very small, but the impulse was large enough so that the force was large enough so that it resulted in a change in the momentum by a finite amount. Now, if you have a system, so it is clear the meaning of the impulse. Meaning of impulse.
Yes, sir.
Okay. What it means that here in this system, so suppose we have a spring mass damper system, a spring mass system, K and M. Okay. Now I am hitting hard with a force. Let us say we have unit impulse force, unit impulsive force, maybe Ft. Okay. Now what it does, that is the change in the impulse is unity. And what happens when you have impulse? So therefore this force is actually, so mx double dot plus kx equal to ft. Now what I am doing, that so this ft is such that ft dt equal to 0 and t is 0 plus epsilon. So for over a very small time interval, I have applied the force, in such that this force is large, but the impulse imparted due to this force over a very small interval of time is 1. So epsilon tending to 0, but still this integral is finite. Now if you integrate both sides, let us say 0 to 0 plus epsilon, and here 0 to 0 plus epsilon, this is dt. What you get from here, from the left hand side, you will get m x dot t equal to 0 plus epsilon minus x dot t equal to 0 plus integral 0 to epsilon kx dt. This, the right hand side, this becomes equal to 1. Okay. Now what you see, one thing here, this position does not change abruptly over time. So because the system cannot jump from one state to another, one position to another position in no time. So there is a continuous, there has to be some time delay before it reaches another position. So if you take epsilon tends to 0, x always remains at 0, because within that small time interval it does not change its place. So therefore we can say that this part equal to 0. At t equal to 0, initially it was at rest, so therefore this is equal to 0. So what this impulse does is that at time t equal to 0 plus, just after the impulse is given, then the velocity is m. So initial condition it was 0, the displacement remains 0, but suddenly there is a change in the velocity by amount 1 by m. Okay, so this is what we have, the sudden jump in the velocity. So what is going to happen to this mass? It will stay there, but it will acquire velocity immediately. So from 0 velocity, it will have a velocity 1 by m immediately. So almost in no time, it will have a velocity, and then the force is not there. Of course, it was there for only very small amount of time. So then after that, it will have a free vibrational motion. So there is no force after t equal to epsilon. So for this impulse function, it had acquired a velocity. After that, its velocity, well, after that, this force is 0. So it is vibrating as a free vibration. So now, if you apply unit impulse, then what we are getting is this. What we are getting is that the problem is same as like x double dot t, x equal to 0, because the free vibration problem. But now the initial condition is that t equal to 0, this is 0, but x dot t equal to, if I say 0, that means 0 plus. Just after the impulse is given, this will be 1 by m. So this problem we'll have to solve to find out the unit impulse response. And you know already that x free t, this was, what was that? This was, this will be equal to, if you recall back, this was x naught cosine omega n t plus v naught by omega n sine omega n t. Because x naught equal to 0, so therefore this becomes equal to 1 by m omega n sine omega n t. So this is nothing but the response of the system due to unit impulsive load. So unit impulse results in a motion which is expressed in this particular form, 1 by m omega n sine omega n t. So this part, sine, except t minus tau, which I will explain why this is coming, why this should come, is that sine omega n t divided by m omega n, this is nothing but the unit impulse response. Okay, clear to you? Is it clear?
Yes, sir.
Okay. So now we consider, now this was unit impulse response. Now, what is the actual problem we are facing? There is a force which is, of course, suppose at, so this is t, and we have now the forcing function ft. Okay, ft is the forcing. And I want to calculate the impulse, this part when t equals to, let us say, t star. At time t equal to t star, I want to find out the response. Okay. So this force can be broken into small component. Like this. So each is like, okay. So I am interested in response at this time instant. But at this time instant, the system has been forced up to this level, t to t star, 0 to t star. So this amount of force has been exerted on the body. Now what is the effect of this body? So the effect will be individually, effect will be the overall effect will be the effect summed up due to the individual excitations, right? This is true because the system is a linear system. Now we come to a very important point. This problem is linear. And for linearity, what we know that the superposition holds. That means whatever the response we get, the response due to a force F1 and response due to a force F2, if you know, then you can find out the response due to force F1 plus F2, two forces, maybe at different time, but you can find out the response due to individual forces by superposition. So that is one thing. And another is linear, and another part, you see, this is time invariant. Time invariant, what does it mean, time invariant? Time invariance means that the parameters of the system is not changing with time. So what it means that suppose you you give the impulse response, you get the impulse at time t equal to, let us say, 10 a.m. Okay, and measure the response, let us say x you measure at 11 a.m. Okay, so you applied an impulse here at 10 a.m. and you measure the response at 11 a.m. So if you give the same impulse, let us say at 10 p.m. and measure the response at 11 p.m. Will they be same? I applied a impulse at 10
Yes, sir.
p.m. Yes. Why? Because by this time the system has not changed. Okay. So if this is time varying system, of course, if you do the experiment now and do the experiment at night, it will matter because by that time the system properties have changed. But here this is time invariant system because the system property does not change with time. So if you do the experiment at 10 and 10 a.m. and 10 p.m. and you get the response at 10 a.m., 11 a.m. and 11 p.m., we expect the same result, same response. So what it means that if I apply a force at this instant and get the response here, apply this force at this instant, let us say tau, and get the response at this t star, it will be same as if you apply the response here at this point, the same response supposedly. So what I mean is this one, if I say that I am finding out the response only due to the impulse here. So at time t equal to tau, I have applied an impulse of certain magnitude, let us say f tau. It's a force, so f tau times delta tau. Let us say that this is delta. Delta is the length. So delta times. Okay, delta. Let me write down delta. So delta ft applied as tau, and I measure the response at this point t star. Now this will be same because the system is linear invariant. If I apply the same f tau at time t equal to 0 and measure the response at, let us say, measure the response at time t equal to t star minus tau. This is clear to you? I mean, do you all agree or not? Because the system is time invariant, so if I take if I apply the impulse at time t equal to tau and measure the response at time t equal to t star, and in the second scenario I am applying the force, same impulse at time t equal to 0 and measuring the response at t star minus tau, and I say that these two are equal. Okay, because as I said that because of the reason that the system is time invariant. Okay, so it is only the difference between the time which is mattering. Okay. So it's not absolute value of the time, but the difference between the time. As I said that you do the experiment at 10 a.m., get the result at 11 a.m. is the same as if you apply the result, apply the excitation at 10 p.m. and measure the response at 11 p.m. So it is only 1 hour difference that is important. And this is here. So if we apply the force, yeah, yes.
What about the initial condition in the original case?
Initial condition has to remain 0 all the time. Okay. Otherwise, the initial conditions has to remain same. So all of them will be applied separately with the same initial condition. Same initial means that 0 initial condition. Because initial condition we are not changing. This impulse means that the initial conditions are 0. So I am applying an impulse that means up to this time initial condition was 0, and suddenly you are applying the impulse. So whenever we take this small element, the initial condition up to this, the response up to this time it was 0. So this is actually I am calculating the response to the individual components, these things every time taking the initial conditions to be 0, so that the overall initial for when we calculate, when we are finished with the calculation, our initial conditions remain still as zero. Okay, there is no change in the initial condition. So now you see that I am calculating the force. So here what I say is that if I the contribution due to the force at t equal to tau, okay, and let us say delta. This is the impulse. Impulse given. Okay, impulse, the amount of impulse given, and what will be the response? Response. So this amount of impulse was given at time t equal to 0. So I want to find out unit impulse response due to this. Well, the impulse response due to not unit but this amount of impulse. And we know that the unit impulse response, and now what I have to calculate? I have to calculate because I am interested in finding out the response at t equal to t star. So if I apply impulse here, so now what I have to do? I calculated unit impulse at when impulse was applied at time t equal to 0. So I have to calculate the response at t star minus tau. So here you see that this response will be 1 by m omega n sine omega n t star minus tau. So this will be the response. And now what we will have to do, this is due to the small impulse over there. Now we'll have to consider all the impulses up to time t star, everything up to time t star, everything will be appearing. And one more thing is important, that this system is actually a causal system. Causal system means that the response at particular time depends on the excitation given at any time prior to that particular time. So earlier we consider only the impulse, only the excitations before that time. So what I want to say is that response at time t does not depend upon its future excitation. For example, if I want to do this, find out the response at, let us say, 10:40 in the morning, I should not consider all. I should consider only whatever forces are being exerted up to 10:45 in the morning. It's whatever I am going to exert in the future time, I do not consider. So if you consider this also the causal nature of the system, then what you have to find out that the response will be the summation, because now the small elements we are adding, and this you have to consider up to t star, only up to t star, because we are interested in finding out the response at t star, and this will be actually over interval. So this is what you see now, is that the response due to any arbitrary excitation with zero initial condition, and that is how we explain this part. Okay, this is clear to you. I should not spend too much time on this because these are all explained in any of the textbooks, so you can just read it. But let me know whether you have at least followed the argument or not. This argument, which I
Yes, sir.
Yes, sir.
Yes, sir.
okay. So here I see. So this is nothing but the response due to the force with zero initial condition. Okay. Now, if we are allowed to write down the response as the summation, because this is a linear. Oh well, the system is, let's say, a cosine omega n t minus pi plus 0 to t and 1 by m omega n sine omega n t minus tau f tau t tau. Just a second, please. I'll just join. Okay, so this will be 0 to t and f tau. So this is the overall response. Now, if you now sometimes in the tutorial we'll solve one problem how to calculate this response. That is how to evaluate the this convolution integral with the help of few problems. But now we will consider another thing which is very important for vibration related problem. That is when the force is Ft, it's in this form. Let us say F0 sine omega nt, sine omega t. It's not omega, or F0 cosine omega t, or any periodic function. With period 2 pi by omega. So any periodic function. So this we consider here, but at this time we'll consider only a part of it. That will let me call. So let me state it again. So what I am going to find out now is that I have the transfer function and I have this Fs, and I want to calculate this. Now what I get is that I put this function, let us say f naught e to the power j omega t in a general form, because if j omega t, maybe a phase difference could be there or not, because this f naught may be considered as a complex number. So what we'll do frequently, that what we'll do is that I'll get the forcing will be, let us say, cosine omega t or sine omega t. Okay. So if this is cosine omega t, so I can write down this as real part of f naught e to the power j omega t, or this part as the imaginary part of f naught e to the power j omega t. Okay. With of course 2 I terms there. So this is the imaginary part of this part and the real part of that one. So we'll do one thing is that I'll consider f naught. So here in this particular situation, I'll consider e to the power j omega t as the force. I calculate the response xt. Let us say I name as x complex. Let us say x star t or x hat t maybe. So when I take the real part of this, so if you have a complex excitation, the response will be also a complex number. But we know already that the force can be a real force only. That means either this will be the real part of it or imaginary part of it. And accordingly, the response will be the real part of x hat or the imaginary part of x hat. So this result I ask you to prove yourself. That is, if you have a response of, so if you have a force which is f naught e to the power j omega t and get the response x hat t, now response due to f naught cosine omega t will be real part of x hat t, and f naught sine omega t, the response will be imaginary part of x hat to t. Okay. So this you prove yourself. It's not very difficult, but this actually helps us. These two results will help us, because from the real domain now we can go to the complex domain and we can study the response with this particular exponential e to the power j omega t, where the manipulation will be easier because the differentiation and integration of this particular function will preserve its nature. So the exponential differential of exponential function is exponential itself, and integration of the function is integration itself. So therefore, everything will be preserved if you consider e to the power j omega t. And at the end, of course, after the manipulation, we can take the real part of the response and the imaginary part of the response. So this particular result is very helpful to us, very useful to us, and we will follow this one. Okay, now, so please take it yourself. So therefore, e to the, so ft, now we are considering ft as f naught e to the power j omega t. Now, if you have that one, then the response. So there is a result which, of course, I'll not prove here, but the result is this. If you have the, let us say, I have a system, well, this let me call this a GS, the transfer function. Usual way of writing, I mean, notation is transfer function, GS, to denote the transfer function, GS. Now, what it says that this result says that if you have this as the input, ft equal to f naught j omega t, so the xt, which I will call a steady state, because maybe this is S, I'll say x steady state, because I am not considering the initial condition. So xst, this will be equal to g j omega times f naught e to the power g omega t. So this result will consider, that is, if you know that g is a transfer function, the steady state response will be equal to g j omega f naught e to the power j omega t. Okay. So let us now say, so this result is important and we are going to use throughout this course. That is, this response, the steady state response is nothing but g j omega f naught e to the power j omega t, when we consider ft input to be f naught e to the power j omega t. So please note down this result. This is very important for us. We are going to use it very often. Okay. All right. Now this response is actually this force. What kind of force is this? This force is actually a sinusoidal or cosine, sinusoidal force, and the nature of the force is, let us say if this is sine, this will be, it will start from here. If it is cosine, it will start from here. So if it is arbitrary, then it may start from, okay, so that will be ft. Okay, ft. And what is the response? So this is ft. What will be the response? What will be the response? Response will be also f naught e to the power. So this is also one term. This amplitude is actually changed from f naught to this one, but the time function is remaining same. So it will be of the same nature, e to the power j omega t. Only its amplitude, that is f naught, this will get modified. So it will have, so it will be something like this, and this will go on forever. So t either going to infinity, plus infinity, or minus infinity, in the same way. Okay. So it will be, the response is like this. So it will be a sinusoidal response because a sinusoidal excitation is given. And here you understand, you know that we are not bothered about the initial conditions. Initial conditions are not taken care of now, because if we are considering only the transfer function and not initial condition. So here, this particular thing, it is not with zero initial condition, but without considering any initial condition at all. So there is no consideration. So this result is valid without considering any of the initial conditions. So this is, there is no, there is no information about the initial condition here. So this is, the force is like that, and the response is also to plus infinity or minus infinity. This is like a sinusoidal response. Okay. Now let us take with this particular now for our system at hand, what we are now trying to find out is the steady state response. This particular response I'll call the steady state response. Why steady state response? It will be more clear when we consider the damping, initiate a little bit of damping there, but at this point we are not considering any damping, so this is the steady state response. And the steady state response here, this will be XST. This is nothing but, well, I should consider hat over there because I am considering the complex force e to the power j omega t. So the steady state response here will be equal to g j omega f naught e to the power j omega t. Now you understand. So since j omega is like that, so therefore xs t this will be equal to f naught. So g j omega, this will be equal to 1 by m. If you put omega here there, so therefore minus omega square plus omega n square, and f naught e to the power j omega t. And then this becomes equal to f naught. So if I consider, so f naught by m divided by omega n square minus omega square times e to the power j t. So this will be the steady state response x s hat. Now if you have x, so if we have force ft sine omega t, then what will be the response? Because sine omega t is nothing but imaginary part of f naught e to the power j omega t. So response here xs will be equal to imaginary part of this response, and that will be equal to f naught by m 1 by m omega n square minus omega square sine omega t. If we have cosine omega t, cosine omega t is real part of this term f naught e to the power j omega t. So the response will be also, the real response will be real part of xs hat t, and the real part of this is f naught by m times 1 upon omega n square minus omega square cosine omega t. So if it is actually cosine function, the response is cosine omega t. If it is a sine function, the response will be sine omega t. That means that there is no phase difference between the response and, well, if there is a phase difference, so if this becomes sine omega t, response becomes sine omega t. Of course, this the amplitude part may change its sign, but apart from changing in sign in this coefficient, there is no other phase change, because if it is cosine, this is cosine. If it is sine, this is sine. But this may be positive or negative depending upon omega is less than omega n or greater than omega n. So we can now sum up this thing. That is the steady state response. I'll consider only the complex part, and this will be equal to f naught divided by m times 1 by omega n square minus omega square and e to the power j omega t. Now what will happen to the overall response? Because this is actually a function, this is the response due to f naught e to the power j omega t, which was actually, the function was from minus infinity to plus infinity. So the response here due to this part, this will be something like this. So this is the part of xs, xst, this is actually, this part will be xst, okay? And now this will go on, right? This does not consider initial condition. you see that the force, the function is like that. So it has certain initial condition which may not be true initial condition. So after that, what we'll do, so I'll have to satisfy the initial condition. This initial condition is not satisfied here. So the contribution of the initial condition, because now the free vibration part, Ft, will be equal to A cosine omega nt minus phi. So this free vibration part will come, and what will be its contribution? The contribution will be such that the initial condition is satisfied. So with this particular one, the initial condition may not be satisfied. In order to satisfy the initial condition, what will happen? That you will have, so there will be another contribution, so that omega may not be omega. So there will be another contribution, maybe here. This one, let us say xft. The xft will be such that, so the initial condition will be the same as the initial. So A and phi, these are unknown quantities. A and phi will be such that the initial conditions will be exactly what is required from our problem. Just one example, small example I'll take, and that will make it clear. Suppose we have the excitation ft as f sine omega t, and the initial condition at x0 equal to 0 and x dot 0 equal to 0, let us say. So this is what the initial conditions are. Now xst, because this is nothing but imaginary part of f naught equal to power j omega t. So x will be imaginary part of xs hat t, and this will be equal to f naught by m and omega n square minus omega square sine omega t. So xs, right? Now our total response x will be xt will be equal to xst plus the contribution of the free vibration, that means without any forcing will come. Why? Because we have to satisfy this initial condition. You see that xst at time t equal to 0, this condition is satisfied, x0 equal to 0. But at time t equal to 0, the velocity will be equal to what? F naught omega by m omega n square minus omega square, which is not equal to 0. So this is not satisfying the boundary, the initial condition. In order to satisfy the initial condition, we need another component, and that component comes from the free vibration part, that means without forcing part, unforced system, contribution from the unforced system, and that will be equal to, let us say, a cosine omega nt minus phi. So now you see that at x equal to 0, at t equal to 0, this is equal to 0, and this will be equal to a cosine, so this will be equal to a cosine phi, and at x dot 0 equal to 0, so this was 0, and this is not equal to 0. At time t equal to 0, it will be f naught omega divided by m omega n square minus omega square, the velocity. This plus this is minus a omega n sine omega nt minus phi at time t equal to 0. So this will be minus sine phi. So a and phi are to be obtained in such a way. So now you see that phi is equal to, so here you see from here that phi must be equal to pi by 2, phi must be equal to pi by 2, and a will be equal to, a is equal to minus f naught omega divided by m omega n square minus omega square. So a and phi will be like this. So out of all this, then what we get, the total response will be the response like this, and because of this part like this is the other part, xf part, so that the overall response will be, now if you add up the contribution will be like this. So if you the velocity and the displacement will be 0 at this point, but it will not be in general. The response will be like this, and it will go on forever, so that the initial condition is now satisfied. This looks a little bit, possibly I did it very hurriedly. I'll explain this again in the next class. But are you getting it? Getting the essence of what I am teaching? Did you get this part?
Yes, sir.
Okay. So next class I'll talk more about this thing, the superposition of two results, because you'll see that the response is not actually, may not be a periodic response altogether. This may be actually an aperiodic response. Yes.
Sir,
Yeah.
can you describe how A and phi are mentioned in the means response graph?
A and phi. So here let us say, so the function is like that. Xf will be equal to minus A, or A, because phi is pi by 2. So therefore it will be cosine like this. Okay. So okay, xf will be then actually I'll have to be careful in drawing this part. So it is something like this. It may not be the same period, because omega n may not be equal to omega in general. If it happens, then there will be some the other phenomena will be appearing, but omega n is not equal to omega. And in general, then there will be two harmonic functions, and they will be superimposed. It will be such that the initial condition, what is desired, that means x equal to 0, at t equal to 0, x equal to 0, and x dot equal to 0, both of them will be satisfied. So this part, this dotted portion will appear only because to satisfy the correct initial condition. In physically, what is happening? In the physical problem, this system does not know that you are applying any numerical tools or like that. So this theorem you are applying or not, that it does not know. But it knows that it has to start from that particular initial condition. So the response will be such that this initial condition has to satisfy, and then it is driven by an harmonic force, so therefore it will have some motion, but this other harmonic component has to appear because this system has to satisfy this initial condition. So, so this is you are asking the A sine omega t. So if you write down A as this part, then A will be appearing over there. A is negative, so that means it will go from this side, other side, not. So you have to. So this is A. A here is negative if omega is less than omega n. So that actually it will start in this direction, so that the velocity becomes equal to 0. Otherwise, it will add up these two velocity. If you if these two slopes, if you have to add these two slopes, so that it gets a 0 slope, because the velocity has to be 0 at this point. So it is only possible if it goes in the other direction. That means it goes in this particular direction. Anyway, so the free vibration part will generate itself such a way that the initial conditions are satisfied. I'll talk about it later on in the next class. But if you have any other doubt, you can let me know.
Sir, this is valid only for linear systems, right?
For
Linear systems.
this is only. Yes, of course. This is only for the linear system, because in the linear system, the initial condition. In the linear system, actually the superposition holds in the linear part. So therefore, xs and ft, so xs and xf, these two actually superpose to give the response xt. So this is true only for the linear system, and I am considering only the linear system in this class. Otherwise, for the nonlinear system, there will be more. The response may be very complex, even if the system is very simple, because this simple superposition principle does not hold. Every case has to be taken up separately. So there is no general theory for nonlinear system, but for the linear system we can generalize the result. We have a general theory for nonlinear system, whereas for the nonlinear system every case is different. Every problem has to be tackled in a different way. Okay, it's in its own way. It depends upon the system they have. But for the linear system we have some theory which is actually quite generally applicable to any linear system. Okay, so this, as you have said, this is definitely true for a linear system. Okay. So I'll talk about this later on, how the two responses have to be added, and then we'll come to a very unique this.
Sir, you are muted. Sir, you are muted.
When you are, well, I never touched it. I don't know why someone started video and then maybe I got muted. So I don't know. I never tried anything. So it got muted on its own. So so that I was saying that next class we'll consider this situation, and after that we'll go to a very unique situation where omega n becomes equal to omega. That means the driving frequency will be exactly equal to natural frequency, and we'll study that particular phenomena in somewhat details. Okay, and we'll see that how our modeling can be changed or to make this response in tune with we normally physically get and what we should get. That these things we'll discuss at length in the next class. So I'll start from this point in the next class and we'll begin. Okay, if you have any problem, any question, please ask me. Okay, otherwise let us now leave.
Yes, sir.
Okay. Okay.
Thank you, sir.
Have a good day. Thank you.